will discuss about trace of a matrix and some problems related to it. So before starting it, I must upload to all of you. Subscribe this channel if you have not subscribed, and share with your friends. If you like this video, then share with your friends, and comment me. If you have any suggestion, then comment me. So let's start. A very important topic, trace of a matrix. So then carefully watch. Consider first a matrix, square matrix. Square matrix. Of any order. Like A is a square matrix. Is any order. I'm taking n order. So it can be in this form. A 1 1, A 1 2. The first one will be, the last element will be A1N. Then the second will be A21, A22, and the second will be, last element will be A2N. In this way, the last row will be, the nth row will be, first element will be N1, first row, nth row, first column, nth row, second column, N2, and last, the last element will be the nth row, An. So this is nth order square matrix. Order is row numbers A and column number A. So what is the diagonal, principal diagonal of it? Elements A11, A22 of any square matrix. These are the diagonal elements. There will be A33, A44. So these elements, the summation of this the diagonal elements are called trace of the matrix A. So trace A is defined in this way. Trace A is equal to summation of A I J such that I equal to J, and if I arise from 1 to n. So if we write down without summation, then it will be A11, A22, A33, and if it is order of nth order, then last element will be An. This is for the trace of the matrix. So some properties I wish to discuss about this. First, that if we will take trace with lambda times of any matrix, then we will find out that we can very easily prove. You can oneself can prove. This is your homework for all of your homework to prove this. Very easy to prove. Take any example and prove. You can prove this. It will be lambda times of trace A. Second property, very important property, this is that trace of matrices or more matrices, trace of two matrices or more matrices A plus B plus C plus dot dot, it is equal to trace of separately, it is equal to trace of A plus trace of B trace of C and so on. This also can be very easily proved. And third is very important, trace of matrix multiplication related to the trace of matrix A and B. This is true for also if matrix multiplication is not commutative, uh, but though it is true. Actually, matrix A B is not equal to matrix B A generally. You cannot because matrix multiplication do not follow matrix commutative law. So that's why you cannot say A B matrix multiplication of A B equal to matrix B multiplication of B A. Cannot surely certainly say. It cannot be equal. But trace is such kind of operation where though matrix multiplication is not commutative, the trace operation is commutative. So it is very important. You can very easily prove this. I am not proving it. We are you can very easily prove this. These are your homework, and if you have any problem, then comment me. I will prove them. Today I wish to discuss about a problem related to linear transformation. So also trace of a linear transformation. What is a trace of the linear transformation? This I wish to discuss. Trace of a linear transformation. I already uploaded a video about it. Linear transformation. So where if T is any operator from a vector space or a field, real or complex, to a another vector field with it is a linear operator actually. Linear, um, uh, it is a linear operator. That's why the vector field must be from the domain set and the range set will be same. So it will operate from V vector space to V vector space. It is a linear operator. I am taking this is of dimension n. Both are of dimension. Then what is the relative matrix with P? So I have already said that the matrix related with T, the matrix related with T, I have discussed it in a video. You can watch this. The matrix related with T is called relative matrix to T. So the matrix related with T, if this is A, we are taking A, say the trace of A is trace of A, trace of A is the trace of T for any linear operator. Trace of T is of T. Actually, if we wish to evaluate the trace of a linear operator, then this is actually is the trace of the relative matrix. Is the trace of the relative matrix means A. The relative matrix is A. The trace of T is the trace of A and relative with the relative to a order basis of the vector field. Relative with the ordered basis, ordered basis of the vector field. Of n-dimensional field. So this lead to this order basis. If we take the if we find out the relative matrix, then the relative matrix trace is called the trace of the linear operator. So I will give an example about this. Let's see. An important thing that is to be find out for any transformation, linear transformation from any vector field Dn, n-dimensional vector field, or actually the field, same field of n-dimensional real or complex. Same. So it is invertible means it is bijective or not. This is a very important question. It is a bijective or not, or bijective or invertible. So for this, we need to find out the relative matrix first. If we cannot uh, uh, cannot justify it that it is invertible or not, then the relative matrix can easily tell you that it is invertible or not. So for this, we need the relative matrix to find out. So there is the importance of the relative matrix. So I used to discuss about a problem which is related with trace matrix also and similar to transformation also. Similar transformation I have already discussed in the video. Similar transformation or similar matrices. Matrices are called similar matrices. If any matrix A can be expressed by another square matrix, both are square matrix, and if you find out a model matrix P such that you can express another matrix your desired matrix. Here B is um, B is expressed, B is transformed into A by a model matrix P. So here we need to find out model matrix. So model matrices are generated by eigenvectors of course. So the eigenvectors of B is very important. Or if you wish to change the any vector to its diagonal form, then if you wish to transform any matrix A to its diagonal form, then eigenvectors are very important to find out, because if the model matrix made of the eigenvectors of the A, all the eigenvectors make the model matrix, and this model matrix transform the matrix into diagonal one. So it is very important form, diagonal form. So I used to discuss a problem. I'm discussing it. A linear operator is given in this way. A linear operator is given from a dimension A vector space R2, two-dimensional vector space, to R2. So here T is defined in this way. T is defined by two elements x, y, is equal to minus y, x. Now I have given the order basis for order basis for this domain vector space is that it is called beta, and for the range space it is beta slash. So beta is also given. Beta is given by, there are very easy standard basis is given. Beta is given standard basis E1 and E2. E1 is 1 0, E2 is 0 1, and beta slash is given for the range space. This is given the different one. One is given 1 2. This is the basis elements for the range space. 1 at 1 1 minus 1. So there are two ways to find out. We have given that we have to prove that we have to find out the relative matrix related with respect to the basis in beta slash. We have to find out with respect to this basis element the relative matrix, and we have to find out in this way that a model matrix find out first, then relative matrix with respect to beta. So this can be found out very easily, the model relative matrix, and we have to find out a model matrix inside the relative matrix can be found out very easily. But we have to find out a model matrix in such a way that we can find out the transformation. We can find out the uh, relative matrix with respect to the order basis this. It is a very difficult question. I am trying to solve it. Let's see this. So you remember this question and doing. We have to given E1 and beta is given. Beta is given that E1 and E2 means 1 0 and 0 1. relative with this relative matrix found very easily. So we have to find out first transformation linear operator of E1. We are given that T is defined by this way minus y x. So you can remember this question. So if we put E1, we will get y 0. This will be 0, 1, and so this can be easily expressed by we have to first find out the relative matrix with respect to the beta. So we express is it through beta 0 E1 plus 1 E2. In this way, TE2 here we find out. This will be if we put here 0 1, then this will be minus 1 0, and minus 1 0 can easily be written by this standard basis minus 1 E1 and plus 0 E2. So now the relative matrix with respect to the ordered basis B beta cannot relative matrix we are find out any with respect to any matrix, but we are find out relative matrix with respect to a basis. This is the importance of the problem, that with respect to a basis we are finding out the relative matrix. This will be the expression through the relative matrix. So these are 0 minus 1, 0 minus 1 will be 0 and 1 will be the first column. This is to be remembered that I am taking 0 and 1 as the column vector. You cannot take as a row. You have to take the column one, and then minus 1 and 0 another column. So this is the relative matrix with respect to the ordered basis, and we have to transform it to the relative matrix with respect to beta slash. So this is the hardness of this problem. So we will first transform this. We will first find out that a yeah, what is the linear operator with respect to beta slash. Beta slash is given. I am again writing in another way. T defined by when I am writing it is given by minus y and x, and now beta slash is given that there are two components. One is 1 2 basis elements 1 2 and 1 minus 1 minus 1. So we need the model matrix P. So through this basis matrix basis we'll find out the model matrix first. How we can verify the model matrix? We define a transformation P. P is now a linear operator from R2 to R2. In this way, we can find out the model matrix. And with respect to this model matrix, we will transform the basis the relative matrix with respect to beta to relative matrix with respect to beta slash. So I will find out P. So first we need to express it P1, 2. It will be P1 2 will be minus 2 1. So minus 2 1 can be transformed. Sorry, I am taking this. This will not be. Here P is differently defined. We will take P is defined as Px is equal to x. So this is another linear transformation. So in this way we will get this 1 2 will be 1. Now we can if we will take it this is E1 slash and this is E2 slash, then this will be. So we have to express it through E1 slash and E2 slash. So if we write 1 E1 slash and plus 2 E2 slash, then it will be expressed by this two numbers. These are basis elements and must be expressed by another vectors. Any vector must be expressed by these two basis elements. So there will be E2 slash. You can verify also that here we will get 1 and here we will get 2. Sorry, actually we have to express it through the standard basis. These are we have taken beta's standard basis is E1 and E2. Beta's standard basis is E1 and E2. So this is E1 and E2. So these are very easily can be expressed. This is one E1 and 2 E2. And the other E1 minus 1 is equal to, this will be again 1 minus 1 and it can be expressed very easily by standard basis 1 E1 minus plus minus 1 E2. This is important because the standard basis to representation for linear transformation. If you wish to find out the relative matrix, uh, iterative matrix for any linear transformation, then it is important that the range vector space basis elements must be expressed by the domain space basis element of the domain space. That's why I have represented it in this way. So now I just express it. I can find out the relative matrix of P. Again, remembering you that 1 and 2 will be the column. 1 and 2 will be the first column, and 1 and minus 1 will be the second column. 1 and minus 1 will be the second column. So this is the P. So in this way we can find out P inverse also, and then can solve this. Inverse will be, determinant will be its minus 1 and minus 2, minus 3. 1 by minus 3 is for 2 to matrix, square matrix, the inverse can be very easily used. There will be 1, so this will be minus 1. For factor of 1 is minus 1 and minus 1 is 1. For factor. And 1 for factor is minus 2. So it's transpose again. Then here will be minus 2. And here will be 2 for factor of 1, minus 1. And then transpose. Then this will be minus 1. This will be our inverse. So if we multiply, then it can be just add multiplying with minus. And this will be 1 by 3. This will be 1, 1, 2, minus 1. And we can very easily now calculate the relative matrix with respect to the ordered basis beta slash. So now the relative matrix with respect to the ordered basis beta slash is very important problem, because here we have given two bases, one beta and beta slash. So beta for the beta, if we find out the if we find out the relative matrix, then transforming it into another or another relative matrix with respect to the another order basis is a difficult one. So that's why it is an important problem. So I have found out some problem. I have found out first relative matrix with respect to the order basis beta first. I found out this. I am writing this. And second, I have taken another transformation P model matrix and defined it in my own way. And defining it, I also represent it through standard basis and then found out the relative matrix of P with respect to the standard basis beta. Then this model matrix and the relative matrix with respect to beta will pursue our here relative matrix with respect to beta is tough one, but not very hard. So P inverse, the model inverse being calculated is 1 by 3, 1, 2, 1, minus 1. This relative matrix I have found out. I am writing again. This is I found out 0, minus 1, 1, 0, and at last the model matrix is matrix 1, 1, 2, minus 1. If we solve this, we'll find out the result. I'm just writing. I've done also. Just I'm writing the result. This will be minus 1, 2, minus 5 and this will be minus 1. So verify this. Must appeal to all of it. Verify this layer and try in your exercise book. It is very tough and very important also. Very important problem of linear transformation. So try it yourself and verify this layer and watch very carefully this video. Very important for visualization. Thanks for watching.